The mathematics of special relativity describe a universe where the distinction between past, present, and future is an illusion. It implies a block universe, a rigid four-dimensional manifold where future events are as ontologically fixed as the past. This geometric fatalism is formalized by the Rindler-Putnam argument, or the Andromeda Paradox. This diagram maps two individuals on Earth. Observer A is sitting. Observer B walks past at 1.3 meters per second. As observer B walks, their velocity vector alters their plane of the present, tilting their now upward along the time axis. At local distances, this time difference is negligible, but across the distance to Andromeda, that microscopic tilt results in a massive shift. The walking observer's present intersects the galaxy 4 entire days in the future relative to the static observer on the bench. If a space fleet launches from Andromeda on Tuesday in the walking observer's frame, but the decision to launch hasn't been made yet in the static observer's frame, the logic of relativity dictates that the event 4 days in the future must already be real. By induction across all possible moving observers, all events, past and future, must equally exist. We are left with a frozen 4D crystal containing all history. This model creates a conflict, a mathematically rigid universe that denies the probabilistic nature of quantum mechanics and the subjective flow of time. The block universe relies on a hidden assumption known as unicity, the belief that there is only one, singular spacetime manifold containing every observer. We can challenge that assumption using the relativistic many-worlds hypothesis. The standard interpretation assumes the static observer and the moving observer are merely viewing the same reality from different angles. It treats reference frames as mere perspectives, but the Lorentz transformations describe an ontological divergence. In this framework, distinct velocity vectors couple observers to distinct overlapping manifolds within a higher dimensional configuration space. Removing the unicity assumption implies the universe is a superposition of all possible inertial frames. This geometry allows for an open future, reconciling the requirements of relativity with the mechanics of quantum choice. To model choice geometrically, we define it physically. A decision is an action. Action requires the application of force, and force results in acceleration. Under the kinematic branching postulate, an acceleration from an inertial frame to a new frame physically splits the world line, creating a geometric branch in spacetime. To test this, we must quantify the distance between the reality where an agent remained at rest and the reality where they accelerated. We call this the degree of separation. We set a decision event at the origin and compare the coordinates of a future probe event from the perspective of the initial rest frame against the transformed coordinates of the newly accelerated frame. This derivation calculates those coordinate differences. By squaring the positional and temporal gaps and factoring out proper time, we arrive at a specific measurement of this multiverse divergence. Crucially, this is not the standard invariant spacetime interval. It is a measure of Euclidean distance in the configuration space, tracking how far apart parallel futures drift based on velocity and time. This equation is the master key to the RMW hypothesis, providing a tool to measure exactly how far apart parallel universes drift based on physical parameters. We can test the behavior of this metric under different physical extremes, starting with the Newtonian limit. This regime covers nearly all human activity, walking, driving, and neural signaling. At everyday speeds, velocity is a tiny fraction of the speed of light. The equation simplifies to velocity multiplied by time. The separation between timelines grows linearly and slowly. Because this separation is microscopically small, the counterfactual branches effectively overlap. They exist inside a coherent zone, allowing for quantum interference between the paths. The geometry changes when we shift to the relativistic limit, applying the metric to high-energy events approaching the speed of light. As velocity approaches light speed, the Lorentz factor in our equation approaches infinity. The separation between the branches explodes. At these velocities, the manifolds become orthogonal. Because they no longer overlap in the configuration space, the physical basis for quantum interference, the ability for two states to occupy the same region, disappears. This physical isolation ensures that no phase information can be exchanged between the branches. The result is a model where high-energy kinematic separation produces the same state reduction we observe in quantum decoherence. Real physical choices are not instantaneous velocity jumps. They require sustained proper acceleration over time. To model this, we use Rindler coordinates, which map the spacetime of an observer undergoing continuous hyperbolic motion. Under constant acceleration, the separation metric grows exponentially. The road not taken moves away from the chosen path at an accelerating rate. This exponential growth results in a causal barrier forming behind the accelerating observer, a Rindler Horizon. As the observer accelerates along the hyperbola, the straight path of their inertial self, the timeline they chose not to take, falls completely behind this barrier. Events beyond this distance can never send a light speed signal to the current observer. The unchosen path is permanently disconnected. Making a physical choice creates an actual event horizon that permanently censors the unchosen path, ensuring the observer's timeline remains self-consistent. This geometric branching model offers a physical origin for the thermodynamic arrow of time. In statistical mechanics, entropy correlates with the number of accessible microstates. In this framework, we interpret those states as the multiplication of distinct accessible multiverse branches. Because any interaction requires momentum transfer, the divergence metric is strictly increasing. To reverse time, every diverging branch in a high-dimensional space would have to converge simultaneously, an event with a probability of 0. This allows us to redefine the concept of free will without violating the determinism of physics. Within any single inertial frame, causality is preserved, and the block universe mathematics remain absolute. This is the geometry of global volition. Agency is the energy expended to rotate your stress-energy tensor and select a new geodesic reference frame. The future encountered is deterministic, but the angle was chosen. Time's forward flow and our sense of agency are emergent properties of surfing an ever-expanding wave of geometric divergence. To be scientifically valid, this framework must provide testable, falsifiable predictions. Standard quantum mechanics relies on environmental interaction for decoherence. RMW predicts a unique additional term, accelerated decoherence. We can test this using a matter-wave interferometer. A particle beam is split into an inertial path and a path subjected to high centripetal acceleration by magnetic fields. When the beams recombine, we measure the interference pattern. If the model is correct, the accelerated path will show a loss of quantum contrast, directly proportional to the Lorentz factor of the acceleration, exceeding standard environmental noise. Synthesizing Einsteinian relativity with multiverse geometry doesn't just solve philosophical paradoxes. It provides a mathematically sound, physically testable framework for the fundamental nature of choice.